Hello everybody, this is week 11 lecture for the Advanced Computer Control MECA 468 and 949. After 3 weeks of content in the Z-domain analysis, the frequency domain analysis for the discrete time system, we come back to the state space representation and the state space design for the discrete time system. So we come back to time domain and use the matrix to represent our system, and use the model, state space model and state space design, observers, feedback to actually to control our system. This part is very similar to the continuous time state space representation. Very, very similar. After all that, you realize, other than some symbols are using different characters, the idea and all the kind of results and all the formulas are all similar. So we're going to go through all these fairly quickly. Just summarize what we already learned so far. Continuous time system. This is a prerequisite, and also some of the content is introduced in week 1 to 6. Professor Lee introduced all these time domain, matrix representation, state space representation of a continuous time system, how to design a pole placement controller with that strategy. We also look at the time domain sampling and frequency domain representation of discrete time system. So it's Z domain, time domain of a sample. The important things we learned here, so probably the most important part of the information is between S domain and Z domain, and between the sample data from time domain to Z domain, frequency domain. So we mentioned many different methods to go through between GS and GZ, and how to do the inverse or forward kind of Z transform, how to do the sampling. So the only thing we haven't learned for this discrete time system is to actually design and analyze the system in Z domain. So analyze in Z domain, and we're not going to do that, so we just ignore that part, and we do everything in kind of design S domain and do the emulation part. So that's done. Another part that is missing is the state space representation for the discrete time system. So now we use phi and gamma, two different symbols to represent system, and you can see there's some relation between A, B, and phi gamma. And also we have to know how to get from frequency domain, Z domain, transfer function to the state space representation and backwards. Also similar information about continuous time is the controllability and the observability and pole placement. All those things are very similar to the week 1 to week 6. So we're going to go through fairly quickly. Firstly, let's take a review of the state space model for the continuous time system. So this is our state space model. One thing I want you to be able to master here is the way that you got state space model. How do we draw the block diagram? So for the state space, we have two equations. One is your state equation, the other one is your output equation. So if we just look at the state equation, the center of this equation is the x dot and x. So always you got this x dot with integration, you got x, that's the center of the whole thing. Then we look at the first equation, x dot equal to ax plus bu. So the input is u multiplied with b, and this feedback is a. So ax plus bu, you got this part is your state space representation. Then we look at the second one. This is our output equation. So the output is y is equal to cx, that's the coming from the state, then du, that's coming from the input. So in most cases, this d is just 0. You don't have that part, because otherwise it doesn't really make any sense. You get input directly connected to the output. So that's our kind of state space representation, and how do we draw a block diagram based on that. And most common way of representing that is using canonical form, because this canonical form has some benefits. We can use this to design our controller, can analyze the system fairly easily, make calculation very easily. There's two different canonical form. The first one is controllable canonical form, which you have, we start from a transfer function here. And we have the last row is the coefficient of the denominator in a reverse order, and also it's a negative sign. And there's 1 here off the diagonal by 1. There's always 1. The rest of them is all 0. That's our state matrix. This is A. B is 0, 0, 0, 1. And C is basically, this is C, is our numerator, the coefficient of the polynomial on the numerator. Also, it's in the reverse order. So this is a controllable canonical form. The observable canonical form, pretty much it's just to transpose. All right, if you look at this, this is a transpose of the controllable canonical form. Exactly, yeah. Then you swap the B and C, all right? You got an observable canonical form. So you should be able to get these forms from the transfer function. If a given transfer function you should be able to do this. So obviously we already know that for a transfer function you can convert to at least 2 different state space representation. And actually there's many more. It's unlimited different ways to represent the system in a state space representation. The reason is you can pretty much think it as we're plotting an object in the 3D coordinate. You can always change the coordinate reference frame and the object will show up in a different way. Although it's exactly the same thing, but because you choose the reference coordinate differently, what you have for that representation is different. So the state space equation are not unique. If you have a one representation with A, B, C, D, and with X, okay, the variable is X, then you can change that to variable X to something called xt, just anything. As long as this t, the determinant of the t is not 0, means t is a full rank matrix. As long as t is a full rank, pretty much you can use the t to do a transformation of the A and B and C. And you get a group of new matrix AT, BT, and CT. And we can write our original state equation with AT, BT, CT, and XT. Alright, so this one and the original one looks different. Okay? When we actually look at it, it's different matrix. However, they are actually the same system. If you try to convert this to a transfer function, you will see, it's the same transfer function. The solution for that state equation, we can use MATLAB to do that, and we can manually derive that as well. Okay, so the MATLAB command for that is called LSIM. The simulation of a linear system, pretty much. If you give it the initial condition, the input variable, and it can calculate the state and calculate output. So you can use the MATLAB. Let's do that kind of manually. Just get a brief understanding how this goes. So normally we start from the state equation. From the input and initial condition, so we say we know our x0. Initially, that's some value, a constant. Then we try to find out what is xt. Okay, so we get from x0, we get from ut. We want to find out xt. We take Laplace transform of this state equation. X dot become xs, so that's in Laplace domain, and minus some steady state error or steady state values. And on the right hand, if we take Laplace transform, x just goes to xs, u just go to us. And now we just make the frequency domain variables x become just capital, and the lowercase x is just in time domain, just to kind of difference this. So over here, we know that in this equation, x0 is given. We know the initial condition, and we know the input. So xs is something we want to calculate. So we just shuffle this around and make xs go to one side, x0 go to the other side, and we got this. So this is basically s minus a, but a is a matrix here. S is a single value, so you can't use s minus a. So s multiply with I matrix, which is the same size as a. Then you can do the normal mathematical manipulation here. On the right hand, this is something we already know. Okay, this is our control signal. This is our initial condition. In most case, or in many cases, this is just 0. Sometimes get some constant values, but these things are what we know. Then the solution in S domain, pretty much we just divide Si minus A on both sides. So solution here is two parts. One is with our initial condition. The other one is no initial condition with the input. So this is coming from input. This part is coming from initial condition. Then we both multiply with Si minus A inverse. We know that the state equation x dot equal to ax minus plus bu. The solution, this is in S domain solution, but normally our final solution need to be in time domain. So we have to take inverse kind of Laplace transform out of this thing. Okay, so after we did that, so we have to convert this into time domain, pretty much. And this, when it goes to time domain, it's called a state transition matrix. And it's actually is e power of at. A is that matrix A over there. Okay, so that's for just this zero input solution. So this is called zero input solution, which is only depends on the initial condition. And the second half here, because you will get S in the Si minus A inverse, and we also have S in the U. So in this case, we do inverse Laplace transform. We can't just do that EAT anymore. it become a convolution. So this is a convolution, become e power of a t minus tau with u tau. Okay, so tau have to integrate from 0 to t. So basically this is why we do the Laplace transform. So make the convolution become just adding. And this is when the time start from 0. If time is start from t0, we can just replace the 0 with t0. So this is kind of a more general term. If time start from non-zero, start from a certain t0. So that's our time domain solution. So we have to keep this in mind. This is going to be useful for us. And we define phi is equal to EAT. So you already see the phi here. Okay, that's just keep an eye on this. We're going to use all this in the next few slides. So method to use this is you define a system, use the LSIM. The system can be any type of model you defined, and U is the control signal, T is a specific time that when x0 has an initial value. So it can be time equal from 0 or time from certain time, pretty much. x0 is the initial value, pretty much. It can be omitted if you don't have this value there. It's just assuming the initial value is 0. You can use this code to run example and see how to build this model and see the output. Okay, so this is kind of a MATLAB solution. Instead of you have to do it manually using Z transform and the inverse Z transform. We continue to solve the state space equation. So the previous slides we solved out xt. So from here we got like what is xt or xs. We haven't looked at this part yet. So if we look at that part, y is equal to cx plus du. So u and x is already given. So we just put what we got from xs in there. And we know the y is actually equal to c si minus a inverse b plus du. So that du part is from here. That's from there. And this is a c xs. So this part is xs. So we can put that in and we got the output ys. If we put that into the final formula, that's this one. When we look at transfer function, that initial condition just goes away because it doesn't change kind of over time. It will disappear with the time goes on. Once we got this representation of y in S domain, and it's actually only depending on the u, the input in the S domain. So we know define our transfer function is output over input in S domain, and it is just this. And you can calculate all this by doing the matrix multiplication, and eventually you come to this one. This is transfer function, pretty much what we have before. And we look at eigenvalue of the denominator, make denominator equal to 0, and the solution is basically the eigenvalue of this matrix A is the pose of the system. So we can analyze the system by looking at the eigenvalues of the A matrix, and the matrix A determine where all the poles are in the S domain, and that will determine the stability of the system, the performance of the system. So A is the most important. Next, going to derive the discrete time state space model. It's very similar, and we're going to use the result we got from the solution in time domain. To derive the discrete time state space representation here, it's quite kind of interesting and magic, you can see. It's coming from the continuous time state space representation of system. So we look at this is a state equation of a continuous time system. And when t is 0, you got this solution. Okay, that's coming from a few slides before. The first part is initial, coming from the initial condition, and the second part is coming from the input. And we're not just interested in certain particular time at 0. Okay, our initial time can be somewhere at the sampling time. So we're trying to think about this system is undergoing some sampling, and every sampling time t, the system is going to update some value. So let's say tk is like last sampling, and we think about this equation turning into this one. Okay, so we start not from 0, we start from tk, the last sampling time, and this t is a little bit larger than tk. We don't make a t very large. When the t is only a little bit larger than tk, and the difference is smaller than the sampling time, we consider it's just a little bit over the last sampling time. For that case, because the discrete time system we use 0 order hold for our input signal and control signal, so in that case, the u signal is actually a constant, because we're using a 0 order hold, and because this actual t is only a little bit larger than the tk. You consider we're between this sampling time and next sampling time. Okay, so in that case, this u is become a constant. This has become a constant. It's not rely on the tau anymore. So when we do integration, we can actually take this outside. We don't have to worry about this in the integration anymore. And we do a little bit rearrangement here. We try to make it simpler, look simpler. We just replace the variable s equal to t minus tau. This s has nothing to do with s domain s. This is just a variable. Okay, so the first bit here doesn't change. The second bit, we just replace t minus tau equal to s. Just make the integration looks simpler, nothing else. This part has nothing to do with integration anymore. Integration, we're doing s or tau, and ranges from t equal to 0 goes to t minus tk. The reason of doing that, you can see here, is this now then tk can be any sampling period, and this part is integration between starting from the sampling tk and gets to close to the next sampling time. Okay, we consider that this is trying to integrate one sampling period and see what happened from that time to the next sampling time. We just change the symbol here. We replace EA with phi. Remember, this is when we got our continuous time solution. And this is a new symbol. We use tau, we use gamma to replace that integration. So gamma replace this integration of EAS from 0 to t. That's the reason we want to replace change. So we sorted out that this is what we have previously. And like I said, we're particularly interested between the sampling time. Okay, so we're interested, well, particularly between the current sampling time and the next sample. So this t is basically this whole thing is basically capital T. When we do this state space representation, we don't use t to represent the sampling period. Actually, we use h. Just to avoid kind of confusion, because capital T in matrix representation normally represent a kind of transformation matrix. So we just use another symbol H to represent the sampling period. Okay, so you look at from top to bottom. This is the next sampling time. This is previous sampling time. You got phi H, and XTK becomes XKH. That's K sampling time. So this will convert from K sampling time to K plus 1 sampling time. Because we're going to write this H over and over again, and most case we can just explicitly say H is a certain constant. It's a sampling period. When we write this equation, we don't actually put H there. We just say xk plus 1, xk, uk. So if you look at that, we just, to avoid these kind of repeating, we just ignore the H. But we know that between xk and xk plus 1, the time in between is a sampling period, H, or sampling time, T. Okay, so our discrete time state space representation is this one. So xk plus 1 equal to phi xk plus gamma uk. And xk is the value of the, say, current or current sampling moment. uk is the input of the current sampling moment. And xk plus 1 is the next state. Okay, it's the next state value. Okay, so we can go from the input and the current state value to calculate the next state value. And also we can calculate the output through the current state value and the current input. And here, if we compare the previous state space representation with a continuous system, pretty much they are the same, other than this A is represented by phi, B is represented by gamma, C and D actually is the same. And definition of phi is EAH. So it's still linked to A, right? It's linked to A. And gamma is an integration. So this part is a little bit complicated. Integration of B with EAS and integration from 0 to H. So gamma is a little bit complicated, but still very linked to A and B. So this is linked to A, this is linked to B. So that's the similarity. Some property of this state transition matrix. State transition matrix is this phi. We call it state transition matrix. It's quite beautiful actually. If we take a derivative of this phi, because it's EAT, exponential of E, and which means the derivative is actually A multiplied with EAT, which is A phi t. So it's kind of very good in computational way. Is taking a derivative of this thing become just multiplication. You don't actually have to do the derivative. And if we look at the gamma, because gamma starting with integration, so the derivative of this gamma actually just remove the integration. You get A EAT multiplied with B, and this EAT is 5, so it's 5B. So the derivative of this state transition matrix phi and gamma is actually equal to itself multiplied with the continuous time A and B model. So it's become very beautiful mathematically. Looks very pleasing. Once we have the representation of phi and gamma, we come to next problem is how to actually solve it. We can do that in 3 different ways. One is numeric calculation using MATLAB. So pretty much we just use a couple of MATLAB commands to do that for us. Second method is called series expansion. So we kind of doing a approximation of E part of X, just using the linear component to represent the complete series. The third method is using inverse Laplace transform, because we know that this is the definition of our phi is equal to EAT, that's this. So we just do the Laplace transform pretty much with that. Okay, then we can go back towards what is this. So we just calculate everything in there. That's the way to go. So firstly, look at the MATLAB. You can set up a system with A, B, C, D, and you just convert it into a digital system. So this can be a digital system. And once you got digital system, you got phi and gamma already, right? With the sampling time h. So this is a way to get it. If we look at manually calculated by hand, the series expansion, we know the formula is phi equal to AH. And E power of something is equal to 1 plus x plus 2 factorial of x squared plus 3 factorial of x cubed. Okay, that's Tyler's series expansion. So we take this part, just take the linear part. Okay, then we can represent like this. Look at this one. So that's pretty much the expansion over there. EAH is I plus AH plus A square H square divided by 2. Then there's a cube H cube divided by 6. And because those are all higher power of H, because H is normally the sampling time, it's quite small. And we approximate with that. Get rid of the rest of that. And gamma is integration of AS. Again, we have already kind of approximate the EAS with I plus AS. Then we can do this calculation. So there's no more power with matrix. It's just multiplication and integration. So relatively like, let's have an example to kind of explain the two different manual methods. How do we go ahead with series expansion and Laplace transform to solve out the phi. In here we have a system in continuous time with A, B, C. Actually B and C in this case is irrelevant, right? What we are after is E, A, H. It's this thing. So it has nothing to do with B and C and D. But anyhow, so the series expansion is basically we've got this formula we derived, use linear components and ignore the higher power in the series. So I is this one, this is I matrix. So I is just trying to match the rank of A. In this case, A is 0, 0, 1, 0, very simple. A multiplied with H. H is only a number, so multiply AH is H multiplied to everything, because other ones are 0, that's just only 1 at this position. Then add them together. This is our phi. Okay, so it's not too hard. It's only involving adding and the multiplication of matrix. And the best we can do here is probably third order system, where the matrix goes very large, and if A got a lot of values in there, this just become very complicated. The second method is Laplace transform. So you can see this is even more complicated. I have something over here to show you how to get the inverse of the matrix, a second 2 by 2 matrix. So I put that there just in case we forget, because you can see here, before we do the inverse Laplace transform, we have to do this matrix inverse. Okay, let's start from Si minus A. That's inside there. Si minus A is I is it's S. I is 1 1 0 0. Minus A is over there on the top. So this is Si minus A, and we have to do an inverse of this 2 by 2 matrix. So we use that kind of table when we do inverse. It's over the determinant, and you swap the kind of this 2 and swap those 2 and put a negative value over there. Oh, you don't swap those 2, sorry. You just put negative value over there. And this is that. So this is the inverse of the Si minus A. So after that, we check the Z transform table or Laplace transform table. You got this is a Laplace S transform table. 1 over S is 1, 1 over S is 1, and 1 over S square is actually T. Okay, and this is look from the table, but T is basically H, the sampling period. Because remember, in the discrete time domain, the phi is trying to link between K to K plus 1. We're looking at the transition with one sampling period. In this case, is a T. So 5 is equal to actually exactly the same thing as what we got. Well, that should be the case, right? It shouldn't be different because we just use 2 different ways to solve one question. Similar to the continuous time system, if we know the transfer function of a discrete time system in Z domain, we got a transfer function polynomial over there, we have the same type of representation for the canonical form. Controllable canonical form, you have the denominator in the last row, get a 1s off the center, and you have a numerator here as C. So this is a phi, this is a gamma, that's C. Exactly the same thing as the continuous time system. The continuous time system, you have transfer function in S domain. This will have transfer function in Z domain. In addition, we also have the observable canonical form. So it's kind of transpose again. You get 5 gamma C. So C and gamma swap, and the new denominator actually goes the very right side of the column. So exactly the same thing if you just treat the transfer function as transfer function. So let's just take an example of these two to write them as canonical forms. So I do that AB's over here just to make sure that we don't misread over this part. And particularly in this case, it have 0, Z plus 0. So actually A1, A2 is 0. Just to be a little bit careful. We don't really read anything over here. That's always 1. You make sure that that's always 1. That's always 1. Over there, that's always 1. Our A1 start from the second power. That's A1. I just be a little bit cautious. That's A2. Yeah. So writing the canonical form, basically just putting these numbers in those matrices. So this one is negative A2, then negative A1, and this is B2, then B1. So this is a B2, B1. This is a negative A2, negative A1. So you need to have actually refer to the formula. Otherwise, very easy to kind of misplace the items. For the second one, that's the same thing. You come up with something like this is a phi, this is a gamma, this is a phi, and gamma. If you see something like this, a lot of zeros, so something might be problematic if we're gonna design a controller for that. Let's look at an example trying to convert the transfer function into the discrete time state space representation. We can do that in two different methods. One is we get a continuous time transfer function S domain. We get our continuous time state space representation. Then we got our discrete time space representation. Alternatively, we can go from S domain to Z domain. Then we, based on the Z domain transfer function, we get the discrete time state space representation. So two different ways. We're going to have a look and compare. So look at the physical model first. So this is a satellite attitude control. Basically, we control the orientation or the facing of the satellite. So the angle of the satellite is YT, that's the output. And the system will actually control the acceleration of this angle. So acceleration with one integration, you got speed. And integrate again, you got the position or orientation. So the transfer function is quite straightforward. GS is equal to YS over US, which is 1 over S squared. We can write the states, say x1 equal to y, so this is x1, and x2 equal to y dot. So from here you already have x1 dot is equal to x2. So just based on this definition, x1 dot is x2. Well, that's it. Then we have to find another equation for x2 dot. That's pretty much. So x2 dot is basically, when we look at here, that's actually x2 dot, right? So x dot is equal to u. So that's pretty much what the state space equation is. In the matrix form, it's just like that. So x1 dot is first line, so it's just x1, x2, sorry. Then x2 dot is basically the second row, is just the u. Y is basically the x1, so y is x1. So that's our state space representation. From here, we got A and B and C. And based on this, we can get our phi and gamma. So we write down this A, B, C here. And these are the formulas we got for phi and gamma. So pretty much we just put this A, B in there and do the calculation. So phi is equal to I plus AH. The higher power, it's a Taylor series expansion of EAH. Or the higher power, we just ignore them. It just can be approached because higher power with H is small, it's just become very minor errors. So this is I, AH. That's what we got for 5. Gamma is integration of I plus AS, then multiply with B, then DS. So this is I plus AS. So remember, this is AS. This is not AH. Just be careful because we have to integrate S to actually get H. So this is I plus AS. This is B. We multiply them together. First row, first column, first row, second row, first column. You got this. And basically, we just integrate each one of them. So S, you got integrate from 0 to H, you got half of H squared, that's from S, and 1 you integrate, you got H. Okay, so you got phi and gamma from this, And the discrete time model basically is xk plus 1 with 5x and gamma u, and this y is equal to ck. Okay, so we did this through getting the continuous time state space representation first. We got this continuous time state space first. Then from A and B, we can calculate phi and gamma. Then we got our discrete time model. Method 2, we have the continuous time transfer function here, and we know there's a zero order hold because this is a plant. This is basically a plant. So zero order hold is between the plant and the controller. So we can use the zero order hold model to actually convert this from S domain to Z domain. So I think this is the question in the tutorial from week 9. That's just putting 1 over S into that formula, and we got something like this. That's our GZ. And from here we got our A1, A2, B1, B2 by looking at the coefficient. Then we can get our controllable canonical form and observable canonical form. Depends on where you put this A1, A2, B1, B2. Okay, so these two basically is transposed to each other, and B and C just swap. Okay, so you got this also another method to represent the state space representation of the discrete time system. And you can see this is not the same as the previous one. As we said, in the state space representation, we will have a single system can be represented in many different ways. So here we got 2 different ways, right? The first is the controllable canonical form. The other one is observable canonical form. And the previous one is not in a canonical form, but we got that from the the continuous time state space representation, okay, from A and B and through the calculation. So is this the same as previous one? We actually can check by do some conversion, or we can kind of do the reverse and get to a point that we'll find out if this is the same transfer. So in discrete time state space model, similarly to the continuous time, we can change the coordinate. We can change the different way of representation. We can change the state by doing a transform. As long as T is a full rank, which means T can be inverted, and you can represent the system either in the coordinate of xk or in the coordinate of zk. And if you get a different T, you can represent in a different way. So this is basically saying as long as T is a full frame or full ranked matrix, so you get T inverse is not 0, or is actually you have T inverse, then you can always do this. Okay, so you can convert from one form of the state space representation to another different form. Okay, this is the relationship between those phi and gamma and B and C, and C and D. So this is a relationship between the phi and nu phi, relationship between gamma and the nu gamma, okay? And it's all here, it's summarized in here. This is how you get all the conversion. And if you're familiar with the robotics, then this is how you actually transfer from one coordinate to another coordinate with the different representation of points in 3D space. Now we look at how do we solve the equation. We have the state space representation here. It might be already very obvious like this. How do we actually solve the x? and y. How do we solve them? Actually, it's here. We have the iterative form in here already. So if we know x0, we know u0, and then the x1 is basically just putting in there and calculate, get a 1. But once you get an x1 with u1, then you can get x2. So it's kind of just iterative, and that's what computer does the best, right? Doing a loop and do iterative calculation. So let's quickly look at this. Xk plus 1 is equal to that. That's from the definition. And then we increase the index by 1. So same thing, you can get xk plus 2 is equal to xk plus 5, xk plus 1 plus gamma uk plus 1. And we go back and look at that. That's our k plus 1. So we replace that xk plus 1 with xk phi plus phi gamma uk 0. So this is just coming that part to fit in here. And we do that over again from x equal to k0 to any k. So phi will, every time you do that once, you get a kind of a power of phi. So the power of 5 is equal to the difference between the k0, your starting sample instant, to the k, your final one. This can be like 5 samples ahead, or any number of samples kind of in difference. So this, if there's 1 sample in difference, you got phi power of 1. If you get 2 sample in difference, you get 5 square, so on. And the rest of them, you can write them together into a summation. So if you look at these two components, this first part rely on the static initial state of x0. Okay, so it depends on initially what xk0 is, and every kind of instant or every sampling time pass, you multiply with a phi. So this is called the part kind of no input kind of response, only rely on the initial condition. The second part is a summation of phi and gamma, but the kind of order of phi and gamma is kind of opposite. So this is pretty much a convolution of this signal. So it's kind of the convolution in discrete time. So it becomes just adding together. So the solution has 2 parts. The second part is actually how we got the transfer function, right? This is the input. So the second part is related to the input. We call that 0 initial condition response. So this one doesn't link to the initial condition, and this one doesn't link to the input. If we just do one step further, we can get the input-output model, which basically pretty much is the transfer function of the system from state-space system. So this is our state-space system. We do a z transform. Like the continuous system. The continuous system, we do Laplace transform. Here we do z transform. So you get k plus 1, representing you have a z multiplied to it. And xk is become xz, uk become uz. Here you have something initial condition over there, rather than just zxz. Okay, so yz is just equal to cxz plus duz. From here we can sort out our xz. So first one will give us xz, then from the second one we get our yz. So xz is just to order that thing, is something like this. So remember the continuous time, what we have in CT, this is Si minus A inverse. This is a continuous time representation. In the discrete time, it becomes Zi minus phi. Well, completely the same. Then you get y is you have 2 parts. This part is linked to the initial condition, this part is linked to the input. And actually this is what our transfer function, hz is basically our transfer function, which is equal to c multiplied with zi minus phi negative 1 with multiplied with gamma plus t. So for the continuous time, it's c si minus a inverse plus multiplied with b plus d. So exactly the same thing. This is when we have initial condition is 0. That's how the definition of the transfer function is. The initial condition x0 is 0, so this part can be ignored. You only get a transfer function. So have another example to calculate the transfer function. Say if we already have the discrete time state space representation. The transfer function, basically we're just trying to calculate this thing, right? I just multiply this thing together. So from here, you got this is phi, gamma, this is c. So pretty much we just plug this in. We calculate zi minus phi. Then we do the inverse. Again, we got this 2 by 2 matrix inverse calculated over here. That's just the inverse. So it's 2 by 2 matrix with a denominator over here. Then you have to multiply with c, which is this thing. Then multiply with b, which is this thing. So just multiply this thing together. And we got hz is half h square z plus 1 over z minus 1 square. So if you check the previous slide, actually this is when we talk about double integer, this is our z domain transfer function. I think the slide number might be wrong, maybe, I'm not sure, but if you go back to the double integer transfer function in discrete time domain, it's exactly the same thing. So here what we did is go backwards. So either way, you can go from transfer function to the space representation, or you can go the other way around. Let's just do the same thing for the second solution. Remember, we have this double integer actually represent in canonical form, two different ways of representing it. So this is another way, and we do the same thing. We use this formula, do the same thing. So that's our phi, this is our gamma, and that's our c. We'll multiply or plug it into this calculation over here. And well, actually that's the same as on the last slide. So if you go back, check the double integer example we just mentioned a few minutes ago, you can see in state space representation, they look different, but once you do this input-output relationship, this is basically transfer function, you find out they have the same transfer function. So they indeed are the same system.